just a quick blurb on the divergence theorem, and next time we'll look at some of the mechanics associated with the divergence theorem. We've actually seen the divergence theorem applied in the plane to a function on a unit disk. Actually, we've seen a version of the divergence theorem. We've seen how the integral of the flux through this curve around the disk is equal to the integral of the divergence integrated over the whole disk. Okay, we've done that example. Now this extends to 3 dimensions so that we, instead of integrating the divergence del dot F over an area, we integrate it over a volume. Okay, well, that's fairly easy to understand. You don't know exactly necessarily what that means because you probably haven't done volume integrals of the divergence, but they're no different than volume integrals of moment of inertia, mass, of any quantity, of electric charge, whatever. And you've done volume integrals of those things. It's just another volume integral, del dot F. Okay, now, just as the integral of the divergence over the entire area of the disk is equal to the flux through the boundary of the disk, the boundary of this volume is a surface. And we integrate the flux through the surface. Okay? And that's a double integral. It's a double integral. It's a surface integral. We integrate F dot N over the surface. And we sometimes call this N ds the vector d capital S. And these are capital S's, not little s's. Little s's go with line integrals. Big S's go with surface integrals. And you can tell by the context which you have. A picture of kind of what this means is, at least the integral of F dot ds, we've got some surface, and imagine this is part of a surface that comes out into 3-dimensional space. And these orange vectors are outward normals. They're perpendicular to the surface at every point. You could get outward normals by doing the gradient of the surface of the function if the surface is expressed as a level curve of a function of 3 variables. Just do the gradient of that function and you have the outward normal at every point of the surface. And otherwise, if you have parameterization like we just did, if you do your t theta cross t phi or your tx cross ty, you'll get a normal vector. And if you do the right cross product, you get the right normal vector. Okay, you get the outward normal. That has to do with orientation. I'm not going to talk about that right now. It's a different conversation. If you get the orientation wrong, your signs are going to get messed up. So you do want to get the orientation right. We do want to talk about it, but right now, let's just talk about the idea that you can find a normal using a gradient, using a cross product of your unit tangent vectors or of tangent vectors, and in other ways. And then you got your vector field, which is just something that might well be given to you. Okay, well, what does it mean to integrate F dot N ds? It means that you take your F function, your field, and dot it with your normal vector, and preferably with a unit normal vector. Okay, don't want to talk about that. Anyhow, if you got a normal vector here, you can project F onto that vector, and the vector projection is, well, the scalar projection is the component of F in the direction of the normal, and that's what you're integrating here with respect to area. Okay, so that's the general idea. And then this divergence thing, okay, whereas curl measures circulation, divergence measures a source of flux. And we'll talk more about what that means, and there's some really good explanations on the internet that I won't even attempt to improve on, okay? But I'll give my own explanations. But this is the theorem And we're going to kind of treat the divergence theorem and Stokes' theorem in parallel, kind of together as we move on. So there is the main idea, though.